Lecture 1 Introduction. Outline computer science at a crossroad. And then computer architecture versus instruction set architecture. And how would you like your CS 252? 252 is the course number at UC Berkeley. And then what computer architecture brings to table, what topics, what job opportunities, research opportunities there are. Crossroads conventional wisdom in computer architecture. We used to think power is free, transistors are expensive. Transistors are invented in 1947. IC is invented in 1953. Okay, and a long time back, every IC has individual package. So every IC is the size of a wheat grain. Very big IC, individual ICs. Okay, I should say transistor. Every transistor has an individual packaging. Okay, tell me today, how many transistors do we have on an IC? The answer is trillions. I don't know how many zeros we have there. And how many ICs in a package? Almost close to 10 ICs in a package. And how many packages in a package? No more. On a PC board, how many ICs on a PC board? On a 1 foot square PC board, how many ICs do you think we can have on there? Well, that doesn't matter because packages have large packages, small packages, a lot of different kinds of packages. But tell me, if we have, what's the old-time computer that you're familiar with? Do you know what CDC is? IBM, it's still there. or maybe Pentium PC. Pentium is out in 1993, almost 30 years ago, 20-something years ago, 25 years ago. Okay, so Pentium PC. How many Pentium PCs do you think we can have on a single 1 square foot PC board? That's not a good question. On a single IC die, how many Pentiums on a single die? The die size remains the size of the thumbnail. Die size remains about that big. How many Pentiums can we have on here? One Pentium on here? Where are you from? It's almost hundreds, close to 1,000 on such a die. 2D layout only. It's not 3D, only 2D. So transistors are no more expensive. From now on, when we talk about a basic electronic cell, the smallest unit, it's no more transistor. It's already a Pentium. Smaller than that, we're not interested in. Okay, so what about power? Long time back, when you have a computer, you look like very technical, very high-end person. So if you want to plug your computer in, turn it on, nobody will question that. You leave it on even after work, after you go home, nobody dares to say anything. So at that time, power is virtually free. Nobody cares about how much power you burn. But these days we do. Why? Especially for mobile devices. So power was free. Transistors were expensive. But new conventional wisdom says power is very expensive. How expensive? Because if you want to burn too much power, then you need to dissipate it. Do you know how to dissipate power? If you have a die here, then you need to fix a big fin on it. Have you seen the heat sink? The aluminum thing? Very huge, a big heat sink on it, plus you put a big fan on it to dissipate power. Okay, plus you need a lot of room, so that you need to have a much larger chassis for your installation. All these are very expensive. So if you want to burn more power on your digital system, then you need to have this, and room, and your electricity bill. Very, very expensive. Okay, for the cell phone, I don't think this is appropriate. So you need to very stingy on using your power, because you have only a very small battery pack in your cell phone. So nowadays, power becomes very expensive in design, in using the device, in whatever. But transistors are virtually free. I tell you, I have 10 billions of transistors for you to use. If you cannot spend all these, then my die will only be used for so much area. And all these will be deserted area. No residents. Okay. Yet your competing company knows how to use those areas. They know what SoC means. They can design both digital and analog circuit on the same IC. They know the process, how to implement that. And they know if they have 2 CPUs, 3 CPUs, even 10 CPUs, how to very efficiently use all these CPUs. And they can even put some other co-processors, put communication circuits on the same die. That's the so-called SoC and multi-core. Okay, they can do that. And you don't have the knowledge, you don't have the technique to do that. So your product becomes very power consuming and very incompetitive. So your company goes bankrupt, you goes jobless. Okay, so that's why power is expensive, yet transistors are now free. Make use of them, or you lose in the battle. So we can put more on chip than can afford to turn it on. We can put a lot of circuit on it, but remember, this will have to be very power saving. Otherwise, everything is in. I have a very good design, but please don't turn the power on. Once you turn the power on, it will okay, because there's no way I can dissipate the heat. So it would self-destruct in 3 seconds. Like what we see in the spy movie. And then the old conventional wisdom says sufficiently increasing instruction level parallelism via compiler innovation. Long time back, we can execute one instruction at a time. So on the time axis, we execute one instruction and then the other and then next and so on. But then we found out that pipelining is advantageous. So we execute one instruction and then start the execution of the second instruction as soon as we can. That becomes pipelining. And later on, we found out that we have sufficient amount of hardware that we can put on the same chip. So why not execute more than one instruction simultaneously and still do pipelining. That's called a superscalar. We can do even better. In one machine instruction, maybe we can pack more genuine instructions in it. Like in one machine instruction, in fact, now I have 2 adds, and 1 multiply, and 1 load. So it's no more just one single primitive instruction. It is already multiple primitive instructions packed in one machine instruction. That's so-called VLIW. Maybe we can do superscalar VLIW. Nobody has done that yet. Why? They're not smart enough? No. The reason is because there's no more parallelism we can find on the instruction level. So the new conventional wisdom says instruction level parallelism has been exhausted. No more. Unless for very special applications. Okay. So law of diminishing, disappearing returns on more hardware for instruction level parallelism. We don't get that much back for the investment we put in. Okay, so the new conventional wisdom says what? Here it says what not to do. But what should we do? What should we do? Multi-threading, or even multitasking, or even multi-users to share the same resource, because this die already has thousands of Pentiums on it for $50 only. Old conventional wisdom says multiplies are slow, memory access is fast. Like 30 years ago, 40 years ago, memory is faster than the CPU. Why is that? Somebody tell me why. How come memory can be faster than CPU? I will have a lot of questions for you. And if I were you, I'll try to answer the questions the instructor raised. That's the kind of practice. Because for now, I don't know you. I don't know your name. And I don't care whether you give me a good answer or a dumb answer. But why can memory be faster than CPU? The question behind this question is, why can CPU be faster than memory nowadays? Do you know why CPU can be faster than memory these days?
Because it has its own memory. Because it has its own memory right on the same chip.
On the same chip should make it faster. You need to speak up so that students in the back can hear you. You misunderstand me. This is CPU, this is memory, right? I only compare the speed of the CPU and the memory. I don't include the communications latency. I'm just saying, how come CPU can run faster? When I say CPU can run faster, I mean CPU can finish a basic instruction within that much time, yet memory can finish and access, read or write, in a much more time, much longer time. How come CPU can be faster than memory? And 30, 40 years ago, how come memory can be faster than CPU? Why?
Because earlier the memory was small.
Many good answers. The best answer is, of course, that's the fact. But we need to understand why. You said somewhat right. Another thing is, memory is always the biggest. because the structure of the memory is very regular. So we always use the largest die size to implement memory. Okay, CPU may be also big because we always want to make CPU very powerful, trying to pack as much capability in the CPU as we can. Okay, so assuming the die sizes are the same. Okay, next, memory structure is very regular. We have decoder. Usually we have row decoder and column decoder using two-dimensional decoding, coincidence decoding. So this circuit is very regular. Regularity means fast. And let's look at the CPU chip also. The circuit runs like spaghetti. Plus, long time ago, we used microprogramming to implement the machine code. So every instruction after decoding will have to go into the control store to invoke a sequence of micro instructions, making it impossible to pipeline, impossible or very difficult to pipeline, making it taking many clock cycles. Whenever we want to use clock, what problem are we facing? You see, in this memory, we don't need to use any clock. Do we? We can, but we don't have to. In here, we do use clock. Why do we use clock? And what problem are we facing when using a clock?
Synchronization.
Right, always wait for the slowest guy. Okay, then why do we want to use clock? To synchronize? No. Why do we need to use the clock? Because things are too complicated. Without the clock, we really can't tell what will happen. Signals just run like a bunch of rats in the city. In every direction, I don't know which rat gets to where first. Okay, things are out of control. Okay, so we have to use a clock in order to manage things, but then we will have to wait for the slowest guy always. Okay, very awkward situation. So long time back, this is much slower than this. Then things begin to change until today. Our CPU is much faster than the memory. Why?
The CPU is more structured than before.
More structured? Right. The clock rate comes from pipelining. First of all, I require that all the instructions are very basic, very simple. Okay, that's first thing. No more complicated instructions are allowed. Secondly, for every such instruction, I also require it to go through a predetermined sequence like fetch, decode, and whatever. Have you heard of those? And finally, I want these stages to be balanced in latency. As a result, we can pipeline the execution of the instructions. So now we're talking about the instruction latency of only very simple instructions. No more complicated ones. Plus, we're talking only about part of the instruction latency because it has been pipe staged. Okay? One more reason. One more reason is due to the IC technological advancements. Now, my CPU occupies only so much area on a die, on a biggest die. The other areas are used for I/O, for cache memory, for whatever. Okay? But for the memory chip, you want to have more memory? Okay, I'll still use the largest chip and pack it with all memory cells. So this thing doesn't get improved at all. Yet this thing uses only a very small area plus all these advantages. That's why CPU is now much faster conceptually than the memory. Okay, so what's the speed ratio of the most current CPU and the most state-of-the-art memory chip? When I say memory chip, you already know I'm talking about DRAM chips. Why? Because memory chips care about storage capacity, and DRAM gives us much better storage capacity. Okay, so even if I don't tell you whether that's SRAM or DRAM or whatever, you already know I'm talking about DRAM. Okay, so what's the capacity of these? Close to gigabit. I'm sorry. DRAM chips still use bits as the basic storage unit. Okay. Very slow? Yes. Speed ratio is from hundreds to 1,000. Slower. So we need to bridge the speed gap. What do? Fortunately, we have so much space available, so we have level 1 cache. In order for easy pipelining, we have 2 level 1 caches, one for instruction and one for data. Why do we split them? Why do we need to have I and D caches? Faster access. Oh, really? No. That's could be one reason, but that's not the best reason.
So the instructions are not mixed with the data, therefore you can just keep reading the instructions, fetching the instructions faster.
Fetching instruction faster, but if data comes in slower, then there's still a bottleneck, and you always wait for the slower guy. So what's the ultimate reason why we use 2 pieces of caches?
They can go on parallelly, data, the instructions.
Well, there is parallelism, but is that parallelism really that advantageous? Because that will waste space too. So if your reason is not strong enough, I won't take it. Plus that increases the cost of my merchandise. You know, our bosses are very mean businessmen. So the ultimate reason is for pipelining. Half of the instructions will do loads and stores. So half of the time, if you don't have a separate independent data cache or data memory rather, then your pipelining will be interrupted. Okay, so if it can help half of the people, why not? Okay, for the second level cache, okay, the CPU will have to wait for longer anyway, so I mix instruction and data in it. Still have space? Okay, maybe even third level cache. But it's still rarely seen. Most of our current products have only level 1 and level 2 caches on CPU chip. Do my lecture make you understand better? Is that the way you want? Or you want me to only read through the foils, making things easier? Always ask me questions, okay? Whatever question you have. Maybe I don't have the answer, but maybe somebody else somebody in here can help you. Or we can refer the question to other courses instructors. He has a question first. Let him ask first.
Could you please expand what VLIW stands for?
Very long instruction word. This instruction word is so long. Why? Because I'm putting a lot of genuine fundamental instructions in one package. Okay, it's like a frame. We fix different types of instructions in the right slot, making every instruction the same length. Okay, very long.
The design of the early CPUs have microprogramming in it. I don't know if microprogramming refers, for example, for the set of instructions like CISC and RISC instructions.
Okay, do you know what is CISC and what is RISC? Complex instruction set computer, reduced instruction set computer. That's not a good name. Those are not good names. Let me give you good names, okay? I would say irregular instruction set. Irregularity comes from length of the instruction, capability of the instructions, and time required for executing the instructions. All don't have to be regular. Okay, so the representative design is x86, Intel x86. Instruction length ranging from 1 byte to 17 bytes. You don't know how long this instruction is. How do you identify a complete instruction? By examining byte by byte. So, do you want to examine all 16 bytes together? Maybe the circuit is too expensive. So you examine byte by byte. So after you can identify a complete instruction, maybe 10 cycles has elapsed. In reality, it's not that bad. Maybe 3-5 cycles has elapsed. Okay? Okay, so that's the CISC. Back to the RISC. I don't like reduced instruction set computer name. I like the other name better, regular instruction set. Okay? Regular instruction set computer means all the instructions will have to have the same length. So your fetching becomes very easy. All the instruction formats are given. OP code, source 1, source 2, destination, immediate. You cannot make too much changes. Almost given, almost fixed. So it's very easy to decode. And all the instructions can take at most, say, 5 steps. Fetch, decode, execute, memory, write back. No exception. But in reality, you have to give it some exception, some flexibility. Okay? So by giving these regulations, you design your instruction set, and other people design the hardware. The hardware can be designed very efficiently, and the hardware can also pipeline very efficiently. Okay. Does that answer your question? Micro instruction, micro coding, right? So for the x86, let me ask you a very important question. Complex instruction set computer. Instructions has all kinds of different capabilities. Almost whatever you want, it has it for you. So you think this kind of computer should appear in recent time or in ancient time? In recent time. Everybody will say that. You can give me all kinds of instructions. So, of course, this must be a current product. But in the computer history, this kind of computer appeared in ancient time. Tell me why. Tell me why.
It's slower.
so it doesn't care about execution speed. As long as this is calculated by an electronic computer, that's good enough. Nobody cares how fast it is. Okay, that's a very good reason. I don't care about the performance. What's the real reason? There are better reasons than that. Okay, let me tell you the reason directly. Remember I mentioned trillions of transistors. Do you know how many transistors we have in the first single chip computer? We call that microprocessor. Intel 4004 in 1971. 29,000 transistors. Only so few transistors. So this thing actually can do nothing. It can do only very simple data movement and arithmetic, logic operations. But you want to like give the fake image of your computer being very powerful to your customer, right? You always need to tell your customer, my computer can do whatever you want. So I have instructions like multiplication. I have instructions like if then else. I have instructions like all kinds of Fortran C statement-like forms. Okay, do you want to do that? Okay, so what 4004 did was, for its 29,000 transistors, it implements very simple ALU, implements only a few registers, implements very simple buses, yet uses a lot of space to write their microcode. So when you have an instruction like if then else, this instruction gets fetched in and it will invoke hundreds of these micro instructions to implement this statement. Okay? Since you're using microcode, what can you not do? All kinds of instructions go into that instruction set. A lot more are added in after every generation. 8008, 8086, 8286, 8386, 8486. Bunch of new instructions are added in constantly. What else can you not do with microprogramming? Okay, but by now you know the implementation of these instructions are so indirect that it must be very inefficient. Later on, we think that's not right. Since we have compiler, since the compiler should communicate directly or instruct the hardware directly, why not make the hardware do its job, play its role, do whatever hardware should do? Okay, so every RISC type machine instruction will go directly to hardware. So for RISC machines, there should be no microcode. Don't give me this layer of overhead. Don't give me this unpredictability. I don't know how many micro instructions my machine instruction will use. Right? You have no knowledge at all. it's regarded as part of the hardware. But in fact, microprogram is software. Okay, so now you know why old-time hardware looks much fancier than recent hardware. Okay, we're back to the nature. We're back to what things are supposed to. Did that answer your question now? Okay, so long time back, multiplies go through this sequence, so it's very slow, and memory accesses are fast. And right now, new conventional wisdom, memory is so slow because we want to have the space, and multiplies fast because we have all kinds of design techniques. You see, our CPU can have trillions of transistors. So what is multiplication? Do you still remember? Multiplication is a lot of multiplicands or zeros added together. If you have one ALU, then you have to add n minus 1 times in order to implement that. But given a lot of transistors, what else can you do? I can do it differently. I can do it in this way. Use one ALU to add a pair, use another ALU to add a pair, another pair. So use so many ALUs to add all the pairs, and then add them again in the second layer, and then add them again in yet another lower layer. And very quickly, I can do partial product reduction, means making the number of partial sums less and less, fewer and fewer, to come up with the final result, to save time. We're even smarter than that. We can filter out these zeros using some algorithm, if you have heard of that, Booth algorithm, modified Booth algorithm, to filter out the zeros, or even to make these two partial products maybe only two partial products, continuous partial products, two partial products, to reduce the number of operands to be added. Okay, modified Booth algorithm. Remember, if you want me to refresh memory for you, I can do that. You want to? Okay, somebody says no, then you must understand it. You do it for me.
No, I just...
Okay, so if this is my multiplicand, it can be anything, and this is my multiplier, something like that. So how many partial products or how many multiplicands do you have to add together here? 1, 2, 3, 4, 5, 6, 7, right? You have 7 numbers to be added together. So Mr. Booth says, no, you don't have to add so many. You can add 1 partial product plus another one here. You see, 7 is equal to 8 minus 1. 31 is equal to 32 minus 1. As long as you have consecutive ones, they always can be replaced by a higher order 1 and the lowest order minus 1. Do you know how to add minus 1? Easy, to the complement. Okay? So no matter how many ones you have, as long as they're consecutive, then I can replace them with only 2 operands. Here comes the problem. What if you have an independent one? Following suit, you'll get from 1 operand to 2 operands. Okay, you lose money. Plus, what if you have interleaved 0, single 0 in between? If you have this then this string will produce a 1 here. Okay, let's ignore this -1. This string will produce a 1 here. And then this string will produce a -1 here. Right? We can combine these two. To this, the red notification, this red sign is like -2, right? -2 plus 1 is like a -1 at this location. Can you still see it? I suppose you can. Okay, so Mr. Booth first proposed this and then came up with some improvements to formulate the second algorithm called the modified Booth algorithm. And I just told you, we can do even better than this. What do I mean? You know addition. The most troublesome thing in addition is carry propagation, right? So we have something like carry look ahead, carry save, carry whatever methods. Do you know what is a carry save adder? Carry save adder says there's no propagation chain. Carry save adder says if you have operands, I'm still looking for white chalk. If a very long operand whatever. If you want to copy this down, you don't have to have the same number. Okay, the carry save adder says every time I do addition, carry save adder. Every time I do addition, I do bitwise addition only. You see, suppose I have these 3 operands. When I do bitwise addition, I get 0, 1 here. Wait, let me write it in this way. I get 1, 0, right? 1, 1, 0. Add them together, I get 1, 0. 0, 0, 1, I add them, get 0, 1. 1, 1, 0. 1, 0, 1. 0, 0, 1. 1, 1, 1. This is a difference. You see, 3 ones, I get 3. 0, 0, 0. Is that fast? No any relationship between bit positions. And what did I get? From 3 operands to 2 operands. In how long? In 1 gate delay time. So suppose I have 32 bits. Then after 1 gate delay time, they become 30 becomes 20, and these 2, I cannot do anything to them, so I have 22 operands left in 1 gate delay. In another gate delay, 21 becomes 14, and I have 1 left over, 15 operands. After another gate delay, I have 10 left. After a few gate delays, eventually I have only 2 operands left. And for the last 2 operands, I do real addition. So I have only 1 real add, plus only a few gate delays to shrink the size of the operands. Mr. Wallace invented this method. And as you can envision, this hardware implementation would be like a Christmas tree. 32 inputs if assuming 32-bit operations. Some carry save adder unit. Then the number is somewhat becomes 2/3 of the original operand number. Some more these units, some more these units, some more these units, and eventually I use a genuine adder. I add only once to produce the final result. The final result may be 64-bit multiplication, 32-bit, 32-bit. The result is 64 bits. Okay, so these carry save adders may become wider and wider. Maybe, I don't know. You need to tell me. And the number of layers is something like a log of 32. I don't know. You tell me. Okay, and this is like a upside down Christmas tree. Who invented it? Okay, so we call this Wallace tree. That's why multiplier now has the speed of an adder. We also need to do some Booth algorithm processing. So multiplication speed is number of clock cycles required for multiplication is a variable from 1 cycle to 5 cycles. And that's all. Okay, so multiplies are fast now. For instance, 4 clock cycles. Old conventional wisdom, uniprocessor performance also follows the Moore's law somehow. So the speed increases like 2 times every 1.5 years. Okay, but new conventional wisdom, now the uniprocessor hits the power wall, the instruction level parallelism wall, and the memory wall. All these 3 walls together, stacked together, becomes an unbreakable wall. So we are not interested in increasing the uniprocessor performance anymore. For the sake of power, we even intend to decrease, to lower the capability of a single processor, but put more on a single chip. So these days, we're encountering the performance increase wall of uniprocessor. No more performance increase. So all this become a sea change, a great change in chip design. Don't overlook the term chip design because everything is eventually implemented using IC. Okay, so the great sea change in chip design is we begin to implement multi-core chips. In 2003, IBM released the first multi-core chip. And today we have a chip with more than 100 or several hundred cores, depending on what core you have. Tell me, what core do you have? Sometimes we have an ARM core and a TI core. It's very likely to be the case in your cell phone. Sometimes we have an army of Pentium cores. Very likely in your server. And NVIDIA also has some controller and shader, yet another type of shader, yet another type of shader. Very heterogeneous core combinations. Okay? And for the most manageable case, if these are all Pentiums, the size of the Pentium army can be over 100 easily. And when you graduate, when you go to work, when you become the manager, the project leader, you should expect to see thousands of such cores in the chip. Okay, so all the research are targeting at 1,000 or more cores. What about million core chip? We'll see that very soon. But maybe never, if not in this year. Because 世界末日 is coming. The end of the world. So we make the cores very power efficient. No wasting. No parallelism is okay with me as long as there is no wasting.
The increase of the number of cores affect for the power consumption.
Of course, more cores will consume more power. So what do? Cut the power line. Power gating. Okay, so even if I have so many cores, I don't have to supply power to every core. I turn the power on only when it needs power. And sometimes it's just standing by. So I can scale the frequency of the clock. Because how do we consume power? Very easy, leakage. There's always leakage all the time. But if I lower the voltage, then the leakage will be reduced. So if it's not working hard, then I reduce the voltage to 1.2 volts to 0.9 volts to keep it alive, but doesn't breathe very well. Or we lower the frequency because dynamic power. How do we consume dynamic power? Charge, discharge, controlled by the clock. Okay, so if I lower the clock frequency, then it will not charge, discharge so often. And maybe right now I'm just using my right hand. What do? Turn up the power of the other parts of my body. So I have only right hand moving. Okay, many things we can do. And I have a low power design, digital system design course offered in the evening. And that's a very important course, but not many universities are offering courses in that kind of that sort. Okay, so now you understand why we go back to 20, 30 years ago design for every individual core. Okay, but added in a lot of power control schemes. Next, let's review the history from 1978 to these days. Single processor performance, big or small, whatever, single processor performance increases slowly up to this point, and then rapidly up to this point, and then slow down again. Begins to flatten off. Reasons. I see technological advancements. Reasons for the same reason, plus architectural improvements. Risk. And then superscalar. And VLIW begins to emerge, maybe even earlier than superscalar, but still not very popular these days. Okay, so pipelining, VLIW, superscalar, all the way up to here until we exhausted all the instruction level parallelisms. Remember, we talk about general purpose processor performance. We don't talk about special purpose. So from here on, no more architectural improvement can be effective, we went back to resort to only IC technological advancements only. So the improvement begins to slow down, and we see the crisis here. So IBM, Intel, IBM first begins to push out the multi-core design. Multi-core design is appropriate for hardware manufacturers because they're just hardware manufacturers. I give you more capacity, and you don't tell me how to use them up because you are not capable of. So all I can do is to duplicate the circuit, to duplicate again. So multi-core is okay for the hardware designers, manufacturers, but not okay for the system designers. Up to today, we still don't know how to smartly use these cores. How long have you been using PC? You. How long have you been using PC? Some 15, 20 years. Have you been using it in a different way these days?
Yeah.
Since you heard of multi-core? No. No. We don't have the suitable compiler for multi-core yet. We don't have the suitable OS for the multi-core yet. We don't even know what kind of cores we need to put on. So one kind of research is if I have a chip like this, then should I use a super powerful Pentium 4 here, and then 2 less powerful Pentium Pro here, and then eventually the smallest, slowest Pentiums here? Or all uniform Pentiums, or all uniform Pentium 4s? I don't know. So many people are doing research on this. Worse yet, where to place the L1, L2 cache memories. Who are to share what? Okay, memories will have to be shared somehow. If you don't share any memory, then your inter-process communication goes down to lower level, becomes extremely slow. So you'll have to share caches somehow. Most often seen case is to share L2 caches, to let them share at the L2 cache level. Okay, next, sea change in chip design. We see this. Only 2,000, many versions. In this version, they have only 2,000 transistors. Okay, and then still use PMOS technology. Do you understand PMOS, NMOS, CMOS? If you don't, you can only do skim research. You never can really have a good grasp of the whole system. So it's like building a house. Do you know cement, bricks? If you don't, how can you build a good house? RISC-2, and then Pentium, and then whatever. This is still RISC-2 plus some co-processors. And then processor is now the very fundamental unit on a chip. No need to look deeper into it anymore. So if I need to have an MCU microcontroller unit, I just grab one from the current design. If I need to have a floating point unit, I just grab another from a current design. I don't do detailed design anymore. Leave those to double E's. Those are just labor work. That's why their monthly pay is lower than ours. Deja vu all over again. It's like something which you think might have happened, and now it's happening again. All right, long time back in 1960s, we talked a lot about multiprocessing. And today, multi-core is nothing but multiprocessing. The only change are the parameters. All the concepts remain the same. Okay? So multiprocessor, imminent in 1970s, 80s, and 90s. We talked a lot about them at that time. On page 5, I'm sorry, I'm too inefficient. Imminent means something's about to happen, but never succeeded. Today's processors are nearing an impasse. Impasse means dead end. Okay? Processors, unit processors, can no more be improved as technologies approach the speed of light. Why 10 gigahertz? After 5 years, can it be 20 gigahertz? Then you need to know, in every clock cycle, how far the light can travel. For 10 gigahertz, how far can the light travel in a clock cycle? Never thought of that? Incredible. The answer is only 3 centimeters. Even light can only travel that far. So electrons in our circuit travel only about 1 centimeter far. Okay, you want to crank up to 20 gigahertz? Almost no way. So that's a dead end. We can see everything increasing according to the Moore's law, but we never can make the basic physics law to increase abiding by the Moore's law. That's the truth, that's the physics. No way we can make changes. Transputer was premature. Long time back, in 1980-something, a computer company called Transputer designed a system called Transputer. It's somewhat like pipeline, many processors in it. But it was premature. It was released, designed too early. Users are not ready. Other technologies are not ready. So custom multiprocessors strove to lead uniprocessors. It is a multiprocessor, and the difficulty multiprocessors are facing is if you have the uniprocessor available, then give me some test chips, test hardware. I need to use these to build my prototype and start to write compiler and start to write OS and start to run benchmarks. And after 3 years, I have an 8-processor multiprocessor. It can run 5 times faster. I want to sell this computer for $3,000 US. 3 million, I'm sorry. But by the same time, uniprocessor speed has increased more than 10 times. Okay, that's why the idea of multiprocessing is absolutely correct, but it never succeeded commercially because it takes time, and the uniprocessor catches up very fast. Okay, so that's why we call it premature. Until today, we have to face it because now on a single chip we can have so many microprocessors. No way we can run away anymore. Okay, so today we must do multiprocessing. We're dedicating all of our future product development to multi-core designs. This is a sea change in computing. And this statement was casted in about 10 years ago. And difference is all microprocessor companies switch to multiprocessors. Microprocessor companies, hardware companies switch to multiprocessors. No exception. So procrastination penalized. What does that word mean? Delaying the release of your product will penalize. And biggest programming challenge is from sequential to parallel. Whether that's 2 or 3 or whatever, as long as you have more than one, then the programming will have to be very, very different, including high-level language programming. And the problems with C changes, algorithms, programming language, compilers, operating system architecture, libraries not ready to supply thread-level parallelism or data-level parallelism for so many CPUs. This number doesn't matter as long as it's greater than 1. And architecture is not ready for so many CPUs per chip. Unlike instruction-level parallelism cannot be solved by computer architects and compiler writers alone, but also cannot be solved without participation of computer architects. This edition of this course using this book, and notice that the 5th edition is out early in this year, okay, just then. Explores shift from instruction-level parallelism to thread-level parallelism, data-level parallelism, and we focus on not only general-purpose CPU design anymore, not only on one kind of conceptual computer anymore. In this book, in this 4th edition, we also focus somewhat on embedded system design and server system design. Okay, but just a very little bit. Okay, computer architecture versus instruction set architecture. Sorry, I didn't give you a break, and time's about up. Well, maybe I'll pause here. Any question?